Hello, welcome back to the new topic. In this lecture gives you the electrical characteristics of MOS transistors. You can see the three-dimensional view of a MOS transistor here in this diagram. In this diagram, the width of the device is W. As you can see from this diagram, width of the device is W from here to here. This is W, and this is channel length from here to here. It is channel length. This is channel length. I am unable to draw this. This is channel length and this is channel width. If you cut a paper, square rectangular paper, that paper will definitely have length and width. Channel is also like a set of papers, example a textbook, rectangular textbook, which will have length, width, as well as some thickness. Now, that is how a channel will be. On the either side of the channel, there will be drain and source. Above the channel, it will be SiO2 dielectric material, which is like a thin film or a plate. Above that, it will be polysilicon or a gate structure. Now, these are the parameters that we have just now seen. L is length of the channel, W is width of the transistor or the channel, D is thickness of oxide layer, that is the distance between gate metal and the channel. Epsilon is the permittivity of dielectric layer or oxide layer. IDS is the drain to source current and VDS is the drain to source voltage. Q is charge induced in the channel. I hope you all know that I is Q by T. Here we apply that relation to estimate the amount of IDS that is flowing through the device. Now, IDS is given by charge induced in the channel, Q, by electron transit time. What is Q? Charge induced in the channel. Why charge will induce? Because of the application of gate voltage. Some charge, some field will establish. Because of that field, a charge will develop. That is the charge. Q divided by electron transit time is the time taken by the charge carriers to move from source end to the drain end or vice versa, which can be written as equation 1, IDS is equal to QC by tau. QC by, or in other words, tau can be written as tau ds, because that is the transit time, that is the time taken by the charge carriers to travel from drain to source. So we can write it as tau ds, where tau ds can be defined as time can always be a function of length and velocity, distance and velocity. As we are talking it as tau ds, what does it mean? Transit time to travel from drain to source. So the distance is distance between drain and source, which is nothing but channel length. So we have replaced that with a letter L by velocity is V, where again velocity, how the velocity on what parameters velocity will depend is velocity depends upon mobility of the charge carrier. Consider consider electron is faster than hole. How faster? Electron is 3 times faster than hole. If we are talking about electron current, we should consider the mobility of electron. If we are talking about hole current, we should consider the mobility of holes. Now mu n and mu p are the mobilities of electrons and holes, which is given here, mu n and mu p, where v is equal to velocity is equal to mobility into the applied field, EDS. If the EDS is very high, the force of attraction will be very large. So mu will be, mobility will be multiplying the force of attraction, resulting in a larger velocity. So that is how velocity v is dependent upon mobility and electric field that is applied between drain and source. Again, this EDS can be rewritten as EDS is a function of length. As see, example, I am giving a mass example. If you stand under the tower, you will get 5 points in your mobile. If you walk away from the tower, the mobile signal strength decreases. So this is a very easy example that every student can understand. That's why I am giving this example. Now the field strength EDS is a function of distance. So here we can write it as VDS by L. Now the velocity, if you substitute this in this equation, now it will become velocity is equal to mu VDS by L. Mu VDS by L. Now that equation can be extended to write the final equation of tau. Tau is equal to L by EDS. So it is L square by mu VDS, which you can see in equation 2. Substitute this equation in IDS relation, you will get mu VDS by L square into QC, where QC is the charge in the channel, charge induced in the channel. There are two conditions. Condition 1 is non-saturated region, condition 2 is saturated region. Because there is no IDS, drain to source current, during cutoff condition of the device, so we don't consider that condition, cutoff condition. There are 3 regions of MOS transistor operation. One is cutoff, another one is non-saturated region or the active region or the linear region. Third region is saturation region. So because there is no IDS, there is no question of having drain to source current during cutoff. We don't consider, we are not discussing that condition here. We are discussing only 2 conditions. One is non-saturated region and the other one is saturated region. Now in non-saturated region, the non-saturated region, let the charge induced in the channel due to gate voltage is given by Eg, field due to gate voltage is Eg, epsilon INS insulator, epsilon naught free space permittivity, W into L are the width and length of the gate structure. Now because channel is under the gate structure, completely under the gate structure, you can take either the gate dimensions or the channel dimensions, both are same. Now QC is equal to Eg epsilon naught epsilon INS W into L. Now that QC should be substituted in the equation to write Vg is equal to effective gate voltage, Vg is equal to Vgs minus Vt. So that if you substitute here, Eg is equal to VGS minus VT minus VDS by 2 divided by D, because the average gate voltage will be VDS minus 2. Now what you need to write is, we are substituting our current relation in this equation. Now when you try to substitute that equation here, what you need to write is Eg is equal to difference of one end of the gate is applied with effective gate voltage VGS minus VT. Other end, the other voltage which is present in the channel is the drain to source voltage. If you take the average one end of the device, at one end of the device, if this is channel, at one end of the device the drain potential is very large, on the other side its effect will reduce, so we can take the average of both. So because the other end is connected to source, is connected to ground, so that is 0. This is VDS. What is the average? Average channel voltage is VDS by 2. So that is the difference between two voltages divided by the distance D. Because as just now we have discussed, E, electric field, is a function of distance. Now that QC can be rewritten as epsilon naught epsilon INS WL by D into VGS minus VT minus VDS by 2. All this is constant terms. Now these constant terms can be replaced with some symbolic equations. See, now that QC is substituted in equation and in IDS equation, that IDS equation results like this: mu VDS by L square into epsilon naught epsilon INS WL by D into VGS minus VT minus VDS by 2. From this equation I'll leave W by L. I'll rewrite all these terms here, because these two terms I need to handle later. This L square, the square of the L, this L cancels this square, and L we can write it here and D we can write it here. We can take this VDS to the end of this equation here. Now the constants epsilon naught epsilon INS mu by D can be grouped and represented with K. K into W by L, width of the device and length of the device, where this is K. I put it here. This is K, and beta is KW by L. Now the relationship IDS has now become beta into VGS minus VT minus VDS by 2 into VDS. That is final IDS equation. That IDS equation can further be written in the form of gate capacitance or unit capacitance, capacitance per unit gate area, that is C0. In terms of C0 also we can write like this. Now as we know, the channel the gate capacitance are the capacitance per gate capacitance per channel is equal to CG. CG is equal to area W by WL is the area of the plate. C is equal to epsilon A by D. So this is epsilon, this is A, area, epsilon A by D. So C is equal to, as per the equation, C equal to epsilon A by D, we have written. We know these terms along with L in the denominator makes K. So that is written as along with mu makes K. So we can replace that with k, because there is no mu here. We have divided mu here. We wrote mu in denominator. Kw by L by mu is Cg. Replace the equation, rewrite the equation with Cg, and where k is Cg mu by W by L, and that may be made equal to C naught into mu. So the final equation of non-saturated region can be written as shown here. Now let us jump into saturated region. In the condition for the saturation region is VDS must be equal to VGS minus VT and above. Now wherever there is VDS in this previous equation, here we have VDS, that should be replaced by the same term VGS minus VT. Now that term has become VGS minus VT whole square here, minus again VGS minus VT whole square by 2. It is something like 5 minus 5 by 2. So what will you get? You will again get VGS minus VT whole square by 2 along with the constants K into W by L. This is saturation current. Similarly, as we wrote in terms of beta C naught, we can again write all the terms in terms of capacitance and all. Now these are the electrical characteristic curves of the MOS transistors. If it is NMOS enhancement mode transistor, whose conduction will start at threshold voltage VT and extend like this. It's non-saturation region, and this is saturation region. This is drain current, and this is gate voltage. The input characteristics. Now similarly, for the same NMOS depletion mode device, for always depletion mode device have got channel has been implanted during manufacturing itself, because there is always channel. The device is always on. For all positive voltages, device is on. If you extend this voltage in negative voltage beyond VT, then only device turns off. Okay, that is how MOS transistors, NMOS transistor characteristics are like this. Whereas PMOS behaves similarly, exactly reverse to the NMOS device. So the characteristic curve, which is in quadrant 1 has now become in quadrant 4 with same parameters, and here also the same. So these are the electrical characteristics of the device. I hope you understand the topic. Thank you.